All right, shows that we're recording. Okay, so this is my presentation on liquid fuels and gas fuels. That was the topic that was assigned to me, so let's go through it. Finally got things to how I like them. Here we go. Hopefully you guys are seeing the full view instead of the picture mode. Oh, come on. Next slide. There we go. Okay. So for this topic, I like this topic just because liquid and gas fuels we use on a daily basis. We use many different types of liquid fuels and gas fuels just in our everyday lives. For example, in the picture left to right, some of us use propane to heat our house. Propane is also used for barbecuing and other features. We all use gas pumps on a weekly basis at least when we fill up our cars. Natural gas is used for not only for stoves and heating elements in our house, but also for the furnaces in our house as well, and for the water heaters that some of us use. So liquid fuels are combustible or energy generating molecules that can be harnessed to create mechanical engine energy. This energy can be used to produce mechanical or thermal energy. Examples are gasoline, diesel, kerosene, liquefied petroleum, gas, methanol, ethanol, propane, and propane I'll get to because that's kind of a tricky one. And there are many other different types of liquid fuels. But like I said, I'll get to propane later just because that's kind of the in-between, as I would call it. I know technical documents kind of say otherwise as to what propane is and what propane isn't, but I'll explain that later. So I mentioned gasoline as one of the examples. This is an example of a four-stroke engine or four-stroke cycle of an engine. And so this is, if you can see my cursor right here. So the intake valve, and I really hope you can see my cursor. The intake valve is here off to the top left. And so that lets in fuel and air as the piston is going down. And, mind you, it starts out this way, but these pistons are moving up and down all the time. And so this is a very, very fast process, thousands of rotations per minute. So, but anyways, the air and fuel mixture comes into the gas chamber and mixes both the air and fuel mixed together. And this is, we're talking about, a lot of combustion that's going to happen in this chamber. So the piston comes down, the crankshaft rotates back up, driving, and this is where right here it'll start, driving this piston back up. And when it compresses all of those gases, the air molecules and gas molecules, what will happen is right here, the spark plug will ignite, igniting the two, because you need air to create fire and you need fuel to create fire. So, and that makes a combustion, which drives the piston back down to a full recycle. And then inside here is all the exhaust gases, and the exhaust gases get pushed out through the exhaust. And so in this example alone, it kind of shows, well, it does show that air and fuel are used to create combustion. And this is, just one of the many examples, like I stated earlier, that, gas is the gasoline that we use in our engines is a liquid fuel. And it's used as a liquid fuel in this example to create combustion inside our engine. So in reality, our engines are just basically a controlled environment of explosions. And these explosions are what give us the power to move the tires and move our cars. Now, diesel engines do not have a spark plug like the previous example that I used. Diesel engines use compression to ignite their combustion chambers. So what happens right here is the intake valve brings in air and fuel just like the previous time, only this is diesel fuel. And so it opens it up, and then as the piston comes back up right here, it compresses all the air and gas together to the point of explosion or ignition, if you will. And then this drives the piston down, which creates power. And then on the reciprocating side of the piston is when it gets rid of all that exhaust, leftover exhaust. And so in this example, in the diesel engine example, we're seeing a fine example of kind of like what we used in class. And I think that's yes. What we used in lab, diesel engines work the same way as a fire plunger did when we used them in our lab experiments, where you know how you took the fire plunger and you slapped it down real hard, and that little piece of tissue paper inside the chamber ignited. Well, it's the same principle as how the diesel engines work, is because the compression rate is so much that it'll actually ignite that piece of tissue, and yeah, so that's how those work. And a lot of what gas and diesel engines, they rely on Boyle's law and Charles' law, in that, you know, when it deals with how pressure, with the increase of pressure, it increases the temperature and other sorts. And yeah, so I'll move on to the next one. I don't have a whole lot of time, but so gas fuels are fuels in gas form. You know, that's pretty obvious. Examples are natural gas, biogas, and propane. And here's the part that I was going to get to as far as propane later. But first, I want to talk about biogas. So biogas is used in, it's kind of like, if you want to think of it as the ultimate way of recycling. So what happens is, you know, bio waste from animals get put into a slurry right here, and then they get chopped up, mixed, pumped into this giant gas chamber, gas tank. And then what happens is all of the, and it's sealed tight too. There's no air inside of there. So they try and devoid it of all oxygen in there. And basically what happens is all of the gas fumes that are coming out of it are biogas. And those can be used to put in generators to create electrical energy, or to or for heat exchangers for thermal energy. Excuse me. Thermal energy for greenhouse gases and other things. Now, so propane, and this is the part that I wanted to get to, because propane is kind of in the middle as far as I can understand. And as far as the studies that I've done, is because liquefied propane is stored at -50 degrees Fahrenheit when in storage. The reason why they liquefy propane is a liquid. And the reason why they store it in a liquid form is because, like for this example right here, gaseous propane is a lot bigger in volume, larger in volume than liquid form. And so, you know, the normal propane tanks that we have, they would be around 270 times larger if we shipped propane in a gas form. And so this is why we ship it in a liquid form, because that way we can create smaller canisters and you still get the same amount of propane out of it. And this is just to maximize the space inside the propane tank. And so what happens is propane reaches a boiling point inside the tank itself. And so when ambient air or exterior air warms up the propane, it releases the gas in here. I'll show you in the next one. It's a little bit easier to see. But so what happens is air, the ambient temperature outside of the propane tank warms up the tank, and it creates gases up here. And so these gases are what fuels our, like for example, our barbecuer. And this right here, it just kind of shows that the more you release your inlet, the more volume of gas you're letting pass through the valve. And this right here, this stage 4, is an example of, what happens when the boiling point of propane, when the temperature falls below boiling point, is that it doesn't release gases inside the propane tank. And so that's when the propane isn't quite working right. In conclusion, we use many gas and liquid fuels multiple times in our daily lives. And I apologize if I wasn't able to go more in depth. I'd really like to, but I'm kind of up against the clock. But we use these daily things every day. And a lot of it has to do with pressurizing them to make them fit where we want them to fit. But not only that, but we use them, it's a better way of storage. And so, like for example, the propane tank, it's negative 50 degrees inside that tank. And as we're using it, as it warms up, that's what the vapors come through the valves when we open up the valves, and that's what heats up our barbecuer. And so, yeah, I hope I explained this very well, and I appreciate. Here's all the equations that we use throughout labs and throughout many parts of the semester. And so, really appreciate all of you, and thank you.